Okay, so this is chapter 23. We're going to do section 23.1 through 23.3. This is the first one we're going to talk about is induced EMF and magnetic flux. We kind of we talked about induction last time, but what we're going to do this time is we have a simple circuit. So our simple circuit has a loop down here at this end. Here's our loop right here. And we're going to put a magnet, we're going to push the magnet into the loop, and we're going to pull the magnet out of the loop. Okay? And if you can see these magnetic field lines, the further away you are with the magnet from the loop, the lower your magnetic flux. And then gradually, as you get closer, the magnetic flux gets bigger and bigger, and therefore you're putting more magnetic flux through the loop, and that will generate a current. Okay, so we want a current to be generated through this loop, and we are measuring the whole thing over here with our ammeter, okay, in the circuit. So it's just one big huge wire and with an ammeter on it, and then we've made a loop, a nice perfectly round loop with some radius r, so that the magnet will fit through it. And so here's what happens. We're going to move the magnet forward into and out of the loop. There's our loop. Now we can do it two ways. We can either move the loop over the magnet, or we can insert the magnet into the loop, okay? So there's two ways to do this. You can take the one is you take the south to north end and insert that into the loop. Okay, so if we insert it in this direction, then the current generated, and think about it yourself, but the current that you generate should go up the left side. Okay, so the current generated should be like that. That is equivalent to moving the loop to the left, and you'd still get a generated current. You'd still get this generated current. Now, if we're coming back out and reducing the magnetic flux, then the current goes backward, and that's the same as moving the loop to the right. Okay? So, if we flip the magnet around, then we get the exact opposite, right? We're going to insert the south end into the loop, and what that's going to do is generate a current in the going down on the left side. And if we remove the magnet from the loop, that generates this current going up on the left side. So, but use your right hand rule. Make sure that all of these things are correct. What I'm trying to say here, because you want to get that. You want to be able to get that right. 50% chance, I guess. Okay, so here's what happens. What we're doing then is we're taking, let's say we have this, I don't want to do the B field in green. Let's say we have a B field that's uniform. And of course, we're going to have loop of some kind. We're going to put a loop in there, a nice loop. Let's make it a nice one. Okay, and then we're going to do the thing with the brushes at the bottom. So that our current only comes from one side. So we're going to make this the length up here, and this the width. And so then if we want, we have our area equals our length times our width. So let's write that, area equals length times width. The normal to A. So you guys remember we need to know what the normal to the A is. I'm going to call it A perp. That happens to be, if the B field is going into the page and this is perfectly laying flat, this loop is perfectly laying flat on the page, then A perp is parallel. It's parallel to the B field. Okay, so then when we do our magnetic flux, which is equal to the main equation is your A times B, your area times your magnetic field, times the sine of the angle between them. All right. Dang it, I did it again. I'm sorry. I did it in my notes backwards, and I'm doing it again. It has to be the cosine of the angle between them. When that angle is equal to 0, then the cosine of that angle is 1. So we're going to be working with our flux is equal to AB. Okay? That is the magnetic flux passing through region A. Okay? So is the magnetic flux FLUX passing through area A. Okay. So this is the main equation, okay, because the normal to this plane of our loop, so this loop, let's give it the area, that surface, we can draw it. We can draw our loop like this. And that has a normal. So if we take a point and then we do a vector that is perpendicular, completely perpendicular to the plane. Okay, so here's our plane. And if we do something completely perpendicular to that plane, the normal to that plane, that is our A perp. And that's the one that tells us what the angle between the B field is. So if our B field is going through our loop like this, and this A is parallel to the loop, then that's what we get. Now, whether it's parallel or not, if it's anti-parallel, so if A perp is anti-parallel to B, then it's 180 degrees. Theta is equal to 180 degrees. And then, of course, your cosine then of theta is equal to -1. So your magnetic flux would then just be minus AB. What that means is the current is just going to flow the opposite direction. Okay, so in one situation, your current flows to the right, and in the other situation, your current flows to the left. Okay? Depending on whether the magnetic flux is growing or dropping. So can we come back here for a minute? So here's the thing. The magnetic flux that is going into our probe, our loop probe, that magnetic flux is growing. When it grows, the current goes to the left. So when it's growing, our current goes that way. So that means our magnetic flux is increasing. When our magnetic flux is decreasing, the current is going back the other direction, that way. And then when we do the negative pole, the opposite end, all we've done is we've flipped B. So our magnetic field, should we do it in, let's do it in blue. So our magnetic field, why did I draw that? I don't want that. I want B, and here B is positive. B is negative. So if the B is negative, our magnetic flux then is going the opposite direction and is negative. So that generates a current that goes in the opposite direction. Okay, so our flux is, to stay with the same symbols, our flux is dropping. And then in this situation, we still have the negative B, but our flux is increasing. Okay, when we withdraw. Okay, so those are all the equivalencies, and this is why the current flows, and it's because our magnetic flux is rising and falling, and as it does, it generates these currents in the loop. All right, one of them didn't get a green circle around it, so now we have a green, everybody's got their own green circle. Okay, so this induces an EMF right? So an EMF has been induced and it generates this current. And so we're going to talk a little bit about that EMF that is induced in our magnetic flux, with our magnetic flux. I want to draw another version of this picture, a better one. You know what? Let's just erase this one. It's not as easy to erase. Okay. All right, so let's draw a better picture. Let's make our area. So there's our area A. We've got a normal to the area. It's kind of pointing towards us, tilted up a little bit towards us. Here's our magnetic field coming in. Okay. And if we look carefully, we will see this angle between our A normal that angle, okay, and then there's this angle, which is equal. So that is the angle that if we wanted to write the magnetic flux out, we would have our magnetic field times our area that it flows through. And we get that in this situation, our area equals our width times our length. All right. And that multiplied by the cosine of theta that gives us our magnetic flux. Okay. And of course, in this case, theta is not equal to 0. All right. Golden. So let's go up here a little bit and talk about Faraday's law of induction. So remember we were talking about a capacitor and the units of a capacitor. So when you're measuring capacitance, it might be some number in farads, right? Well, this is the fellow for which the farad comes after, okay? So this is our capacitance. A farad is named after Faraday, so he's a big guy in E&M, electromagnetics. He's he's like the George Washington of electromagnetics. So what Faraday did was basically what we saw up above. And he noticed, Faraday noticed that an EMF was generated when changes in the amount of flux magnetic flux occurred, 2 R's, 2 C's, I don't remember, occurred in a given area defined by the conducting wire. So all I'm saying is the first person to do this type of stuff was Faraday. Okay, so Faraday did essentially this type of experiment, and he noticed the induction that happened. So that helps everyone in the world because he took his information and he wrote it all down. So Faraday found 3 things. 1, he found that the EMF is proportional to delta phi, so the change in phi, okay? The second thing he found was that the EMF was proportional to the amount of time that it took, inversely proportional. So this is directly proportional, which means there's some constant in there that he doesn't know. This is inversely proportional. And then 3, the number of loops it's directly proportional to the number of loops. So if you increase the number of loops, you're going to increase your EMF. All right, so he's got these things, and if that's the situation, then he said, well, we can add a constant if we want to, or we can just lay it on out there and say that those 3 things combine to give us the magnitude of our EMF is equal to the number of loops times delta magnetic flux over delta time. And of course, delta time just equals our time, right? That we measure this situation. And I don't like how I wrote the flux. So let's do that again. So magnetic flux. Let's just do a little thing on magnetic flux. This is the symbol for magnetic flux. This is capital phi. Lowercase phi looks like this, or sometimes looks like this. I do it both ways, depending on what I'm looking at. This is typically an angle, and this is other stuff. So capital phi, okay, that's magnetic flux, all right? And if we go and we look at units for magnetic flux, then we get right here, we have Teslas times meters squared, right? So that has to be the SI units of magnetic flux. So magnetic flux, the units are Teslas times meters squared. Okay. You know what? Capital Phi looks like Darth Vader's TIE fighter in Star Wars. Although, wait, no. Darth Vader's went like this, right? He was the only one that had the one that went like this. All right. Well, the regular guys, all the regular guys had TIE fighters like this. Darth Vader was special. You know what? I don't like Darth Vader. Okay, so just a regular TIE fighter on its side, spinning around. So I'm going to write down the actual equation. Here we go. So we've got our EMF, and we've got our number of loops. We've got our delta phi, and we've got it over time. And we need to write a minus sign. And the minus sign is where the directionality comes in. So if we notice up here, we were generating more as we insert. Let's look at case 1, okay? So we're looking at this case right here. We're inserting the north end into the current loop. The flux is increasing, okay? Our flux is increasing right here. And as it's increasing, the current generated goes to the upside on the left. So what we're saying is here's the thing. We're increasing our magnetic flux through. But what does that current want to do? That current has to be generated such that it wants to equalize the situation. I'm going to clear out the inside of this loop so we can do some work with the right-hand rule. Put your thumb along this current that is not this current. We want the current going to the left. On the bottom side, going to the left, coming up the left side, okay? So put your thumb along that current, and then what does that force the magnetic field to become as that's going up that side? It forces the magnetic field to go into the page, okay, on that side, and out of the page to the left of, on the outside of the current ring. So it's going into the page. Well, that's interesting because we're increasing our magnetic field going through. We're increasing it with our magnet. As we insert the magnet this way into the loop, it's increasing our the density of our magnetic field. Therefore, our magnetic flux is going up. But what is the current doing? It's fighting it. it's pressing the current, or it's creating a magnetic field that goes the opposite direction. Okay? That is our induced magnetic field. So it opposes B induced opposes the flux. So the B induced is a flux as well, and that flux is going down, trying to reduce the amount of flux going in. Okay, so it's like nature trying to create friction, balancing it out. Okay, so this is the friction that is coming about, trying to slow down the situation, right? It doesn't like what's happening, and it says, no, we're going to create a magnetic field going the other direction, which is basically creating a flux going the other direction, which is fighting, and that fight gives us this negative sign. Okay? So the fight is something called Lenz's law. So Lenz, this fellow, Lenz's law. And if you want to look at figure 23.7, it's a good diagram describing Lenz's law. So I'm going to try and recreate a similar drawing. Hopefully I'll be able to get Lenz's law in here. All right, so first of all, we have our bar magnet. So here's a north, here's a south. We've got a current loop. So I'm going to bring it up. We're going to draw a loop. We're going to bring it down. Okay. We're inserting this guy into there. Of course, we've got our magnetic fields happening. Right? Great. Now that you could do it two ways, of course. You can, well, let's just keep it simple. This guy going into, so our magnetic flux from the magnet is increasing. I wanted to say a current or an I. So a current I is generated to oppose the increase in phi and a magnetic field opposing, so it's the magnetic field of the loop opposes the B of the magnet. It's this opposition that Lenz was getting at, okay? But every single thing that happens so that, so let's draw the magnet so we can see that we can see which side is positive. So here's our north side, here's our south side. So the magnet's going through the loop. And so we can see that the loop is going this way. And as we're doing that, once it's inside there like that, of course, the magnetic field we've already seen is roughly the same, right? However, as it's being inserted in this direction, the current wants to go this way, and that generates a magnetic field from the loop that is going that direction, okay? If you do your thumb along the current and you put your fingers into the loop, they point down, okay? So that's into the page, all right? So that, even though the B field is going this way for the magnet, so that's B magnet, this B loop opposes it. Okay, that's not confusing at all. But this is what happens, and we need to keep track of these things. And when we were doing the homework, when I put out the homework, this is the induced and the fighting of the, we're basically looking at Lenz's law and how things get generated to reduce and minimize effects, okay? And electromagnetism, magnetics is just the spin-off, okay? So let's talk a little bit about how do we use Lenz's law. All right, well, first you need a good drawing. You need a good drawing. And hopefully that's what I produced here. And if not, the book has good drawings. Okay. All right, so second, we need to determine the direction of the stationary magnetic field. So the original magnetic field in our case was from the magnet. So that's the first thing. So we determined that the magnetic field is going to go in that direction. So determine the direction of the original slash stationary magnetic field. And give it a name. Name that thing. So in our case, we're naming it B magnet. Okay? Then, third, determine. I want to say figure out, but determine is a better word. Figure out if your magnetic flux through the loop is increasing or decreasing. Okay, because if it's decreasing, we already know what happens. The current generated goes in this direction, okay? So if it's increasing or decreasing, that matters, all right? And so that's third. Fourth, determine the direction of current and thereby, you guys love the word thereby, using the right-hand rule, you are determining, and thereby using the right-hand rule, get the B of the loop. Okay, so of course, if our current is going this way, if the phi is decreasing, then that generates an out of the page. On the inside of the loop, it generates an out of the page current, okay? So if we're going this way with our current, then this gets generated, and if we're going this way with our current, that gets generated. Okay, so far so good. Of course, notice that it's opposing it, right? It's opposing the magnetic flux, whether it's going up or down, the B loop opposes that. Okay, so to get the induced current, we must have an induced EMF. So that's EMF, and you can induced, or you could say EMF, well, I don't know how else to put it, just EMF induced. That is what generates the current. So it's an induction. So Lenz's law is all about induction and inducing a current in a loop. So how do we calculate? Let's do an example. Do a little example here. So this is straight up example 23.1. And we're going to calculate it, and of course we're using figure 23.7. So I'll draw again a magnet. We've got a south pole, a north pole. We're putting it through our loop. Okay. And we've got B field all over the place. And as we put it through, of course, a current gets generated in that direction, okay? And let's say that we have, on our loop, we have a radius r, and we're given that r is equal to 0.06 meters. We only have one loop, so n equals 1. What is our area? Area equals pi r squared. And if you do all of that, you end up with 0.0113 meters squared. Our initial magnetic field, when we start off, we only have a little bit of magnetic field going through the loop, okay? Just a little bit. And then gradually, as it moves forward, it's going to get a lot more dense as we push forward, okay, into the loop. So that density is going to increase, and it's a pretty strong magnet. So our B final equals 0.25 Teslas. Okay, so two different things there. All right. The amount of time, how much time did it take? So T is equal to 0.1 seconds. I'm supposed to use delta T, but I think you guys get it. So we're just going to do T. So let's write down I initial is B naught A, and our we're perpendicular, so our B field is perpendicular to A perp, okay, from the magnet. So since that's the case, the cosine of theta is equal to 1, so we're not going to put a cosine theta on there. We're just going to leave it. And let's do our I final, or flux final, phi final. That would be, again, cosine is equal to 1. So we have our B final times our area. And now, of course, delta anything is equal to whatever that thing is finally minus whatever that thing is initially. So delta phi is equal to, I'm going to pull out the area, and I'm going to say that that's the area times the final field minus the initial field. Great. So we've got that, and now we can use our equation for the EMF generated, induced. Okay, so this is induced in the wire EMF. That's equal to minus the number of loops, which we know, our delta phi over time. So we can insert all of those. Let's just do induced instead of EMF there, and that makes sense. So we've got our minus 1 times 0.0113 times our 0.20. I calculated this, okay. Basically, we're taking this final and subtracting off the initial. Delta B is equal to, and this is delta B right here, by the way. Delta B is equal to 0.2, 0 Teslas. Okay, so we've got our delta B, and then we're going to divide by our 0.1 seconds. And this is meters squared. But it doesn't matter because all of that equals voltage, which is an EMF. That's our voltage. And that gives us a negative 22.6 millivolts, okay? So we're asked really for the induced magnitude. So this really is the answer because you're taking the absolute value. And you're getting 22.6 millivolts. Not difficult. That generates a current in the magnetic field. So the next thing, how else can you do this? Well, any change in magnetic flux for that area surrounded by the wire results in an EMF. Okay, so since any of them result in an EMF, and the EMF, I should say, results in an EMF that opposes the change. It opposes the change. Of course, we're using Lenz's law to do that. Well, how else can you get a change in EMF? You can change, let's draw a loop. A rectangular loop. And we've got our wires like this, and we just lay down a conducting bar across this thing, and we're going to put a B field in here. So B field into the page. I don't even know if I drew it into the page or not. Yeah, I did. Okay, so here's our uniform B field. And of course it continues this way. All right. We can slide this guy back and forth. What does that do? That changes the area, right? So there's this length from one side to the other, and if we say this is our origin and this is the x direction, then from the origin we're going to get, let's say we move it from that place to this place. So here is x naught, here's x final. We've changed our area. So since phi is equal to b, which we know is uniform, we're changing our area. Okay, and then of course the cosine of theta is equal to 1. So we're changing our area, and that gives us a change in flux. So this is called motional EMF. It happens in different ways, okay? The Hall effect is a study of the force that comes from a moving charge in a magnetic field. But this how do I want to word this? This is, we're looking at what happens when we change due to the changing the area. Do, not do. Due to a changing loop area. Okay, so that's the scene. And of course, that cosine of the angle doesn't have to be zero all the time, right? It could be that the B field comes in askew, right? So the B field might come in askew. That's fine. It doesn't matter. You figure out what that theta is, and then, of course, the real equation is B delta A times the cosine of the angle. And theta is just the angle between A perp and B. Okay. Good. So let's do an example. Well, we can go back to our drawing. Okay. Instead of, I'm going to make our delta A. I want to make the delta A positive. So here's our x initial, here's our x final. And so x final minus x initial is going to give us a positive. So let's do that. It's moving with a certain velocity. Okay, so what is the question is, if the bar is moving at velocity v, which is equal to delta x over delta t, and we know that a is equal to whatever x is times L, then our velocity is equal to x final minus x initial over time. Our delta A is equal to our length times delta x, which is equal to x final minus x initial. And therefore, delta x is equal to v times time. And I'm just going to substitute in v times time there, okay? So our delta A, this is what we really want in the end. Delta A is equal to our length here. This, you can call it a width, but it's the length that the bar has to reach from one wire to the other, times the velocity times time. Okay, you can see delta x is equal to vt right there. Okay, that's just that. All right. Let's continue. So let's just continue. We now have delta phi equals our b times our delta A, and then, of course, times the cosine of the angle between them. That's the main equation. We are working with theta equals 0, so we can now step back and do delta phi is equal to our b, and then I'm going to write LVT for our delta A. Now, I wrote the t as, t, but I really should have written it like this, because you'll see why in a second. Because if we remember that our EMF induced, let's write it as induced, our EMF induced, okay, that equals our N times delta phi over delta t. Well, if we take this equation and we pull out that, then that's just equal to our magnetic field times the length of the bar times the velocity of the bar. So we can then say that N times our BLV is equal to the EMF induced. And that is motional with this situation, okay? It's this situation, which many problems are created using this situation. So In fact, these problems are in the homework assignment. So this all works only if, so this works only if we have a B, our magnetic field, is perpendicular to our length, which is perpendicular to our velocity, which again is perpendicular to our B field. Keep in mind that the B field and the area are also perpendicular to each other. I mean, parallel to each other. Okay, so A is parallel to B. So all of this has to be the case, otherwise we have to insert this cosine of theta, okay? But if that's the case, then we get this equation, okay? This sweet, sweet equation. So let's do an example. This is motional EMF, and we're using figure 23.12, and this is the same as what's the problem in the homework. So here we have our spaceship. I'm really good at drawing spaceships, and I'm super patriotic. And up here we have the satellite that it's connected to. Again, looks like kind of like a TIE fighter, I suppose. Let's give it solar panels. I'm all about solar panels. Okay, there we go. And then this is the conductor. We've got current flowing this direction. And then the current returning comes back through the ionosphere in the form of ions. So the current returning, I kind of think this is kind of hokey, because who knows what this exact area is. However, the B field, if I remember right, is going into the page. I can't remember. It doesn't matter. Well, it kind of does, but all we're looking for is the total EMF. So one way or the other, whether it's into the page or not, if it's positive or negative, we don't care, because we're taking the absolute value of the whole thing. So I'm drawing them into the page. I might be wrong. I can't remember. Okay, so here we are. We're given that our length is equal to 20 kilometers. Let's write that out in let's write that out in meters. That's 2 times 10 to the 4 meters. All right, our velocity is huge, 7.80 kilometers per second. So let's write that out as 7,800 meters per second. And then, of course, the magnetic field of the Earth equals, let's just call it BE. And we're given that it's 5.0 times 10 to the minus 5 Teslas. Okay. The question, what is the EMF induced? So we'll just call it EMF induced. In this situation, so fine, let's do it. We've got EMF induced is equal to BLV, and 5.0 times 10 to the minus 5 times 2 times 10 to the 4 times 7,800. That is 7.8 kilovolts. Okay, so that does it. Hopefully you have everything you need to do your homeworks and homework problems. If that didn't help, if this doesn't help you, email me. Okay, I've had a few emails already. Hopefully I've uploaded something that's super helpful, and because I did the hints for this homework assignment prior to this to help. Okay, so that's it for today. Thank you.